Good morning. We are now looking at the worked out examples in chapter 13. So here is a sample problem, and we are going to start classify each of these two molecules. We have two molecules. They are monosaccharides, and we have to classify them as aldopentose, ketopentose, aldohexose, or ketohexose. Looking at the names, aldo has an aldehyde group. Pent has 5 carbons. OSE is a monosaccharide, a sugar. Ketopentose, keto is a keto group. Pent is 5. Monosaccharide with a keto group and 5 carbons. So now I'm looking at the molecule ribulose. So I have to see how many carbons first. 1, 2, 3, 4, 5. 5 carbons is pent. So this is a pentose. Is this a ketopentose or an aldopentose is the next question. So we see a keto group. So we will classify this as a ketopentose. We will look at this molecule, 1, 2, 3, 4, 5, 6. 6 carbon, hexose. Now is it a ketohexose or an aldohexose? We will look for the aldehyde group. It's an aldohexose. So ribulose has 5 carbons. The analysis we have set up. Now this is the next problem. Now we are going to classify this, a monosaccharide, as aldotetrose, ketotetrose. So let us see how many carbons. 1, 2, 3, 4. 4 carbons. 4 carbons is tetra. Tetrose. Aldehyde. Aldotetrose. For each of the following indicated with a carbon in red is chiral or achiral. Chiral, achiral, we are going to look. How do we identify a chiral carbon? Non-superimposable mirror image. And every carbon that is chiral is attached to 4 different groups. So here I'm looking at carbon, 2 of the same groups, 2 of the same are attached to this carbon. This is achiral. I'm looking at this carbon, 4 different groups are attached to the carbon. This is a chiral carbon. Here I'm looking at the carbon with 3 groups. So for a chiral carbon, you need 4 different groups connected to the carbon. And that produces a non-superimposable mirror image. So let's see. So this is the solution for this sample problem. So we are given this molecule, and we have to pick out. There are 2 chiral carbons in this condensed formula, and we have to pick out those 2 carbons. So I'm going to start with this carbon. This is connected to this group, this entire group, but 2 hydrogens. So they are the same. So this is achiral. I'm moving to this carbon. There is 1 hydrogen, 1 OH, this group, and this. So there are 4 different groups with this carbon. So this is our first chiral carbon. This is the second carbon. There are 4 different groups. So this is our second chiral carbon. So again, for a chiral carbon, you need 4 different groups attached to the carbon. So that makes it a chiral carbon. Now this is chiral, achiral. These are the Fisher projections. So we are looking at these Fisher projections, and we are going to determine if it is a D or a L isomer. So I am going to look at the OH. These are the OH. First we have to see if it is chiral or non-chiral. So I'm going to look. This is where the carbon is located, at the meeting intersection of the vertical and horizontal lines. So 1, 2, 3, 4 different groups. Chiral, carbon. These 2 are similar groups. Achiral. So I'm going to look at this chiral. Only if it is chiral, we'll determine a D or L. stereoisomer. So now to determine, I have to look for the position of the OH. So OH to my left, OH to my right. That's what I look for. So in this, the OH is to the left, drawn to the left. The mirror image is drawn to the right. So what do I say? The carbon is for, therefore, it is the L stereoisomer. The carbon to the left, L stereoisomer. And we have to draw the mirror image, which will be the D stereoisomer with the OH to the right. So the L isomer is the OH position to the left. The D isomer is the OH position to the right. Now the second molecule, as we determined, was the achiral carbon. So again, the carbon at the intersection is attached to 4 different substituents, making it chiral. It is the L isomer. The OH group is drawn to the left. The mirror image is the reverse, the OH to the right, and that is your D isomer. Again, does this Fischer projection represent D or L? OH drawn to the left, it is your L stereoisomer. So that's how we will determine DL. This is the Fischer projection, D or L. How do you determine D or L? So we are going to go to the furthest carbon atom. From the carbonyl group, we will walk away to the furthest carbon atom that's chiral, which is this. This carbon is achiral because it is attached to 2 hydrogens, 2 of the same. So this is my furthest away chiral carbon, and the OH is drawn to the right. Okay? So now the solution, analyze. Number the carbon chain starting at the top of the Fischer projection. Chiral carbon 4 has the highest number. It is furthest away. The OH group is drawn to the right, which makes it D isomer, D. So that is the process of thinking to determine a D or L isomer if you have more than 1 chiral carbons. So again, this is how the solution is continued here. We start numbering and go down furthest, the chiral carbon atom with the highest number. Draw the Fischer projection for the mirror image. So this is D. So if you have to draw the Fischer projection, the reverse, L isomer, so this is where you are going to switch the OH drawn to the right to the left, and that will make it the mirror image for this particular molecule. So the next problem, Haworth structure. Found in immunoglobulins has the following Fischer projection. Draw the Haworth to show beta D manners. So first, let me see how this is D. Starting to number the carbons, I come to the furthest carbon and look for the OH drawn to the right. That makes it D. So I have to draw the Haworth structure to create a beta isomer. So turn the Fischer projection clockwise. Then take this OH and fold the molecule and connect the O to the C by folding the molecule this way, creating a hexagon. So fold the horizontal carbon chain into a hexagon, and you bond the O to the carbonyl group. The OH goes here. So how do you set up the alpha or the beta isomer? Draw the new OH group above the plane, above the ring. So if you place the OH above the ring, you are creating the beta isomer. If this OH is drawn below the ring, you have the alpha isomer. To set up the beta isomer, you have to make sure the OH is above the ring. Draw the Hayward structure for alpha D mannose. So you have the same. The next question, we can come back and see we do the same process, but the OH is below the ring and the hydrogen is above the ring. So if you turn it around, you are creating the alpha stereoisomer, and that's the Hayward structure in this particular sample problem 13.5. Why is D-glucose called a reducing sugar? Remember we said that in Benedict solution, the aldehyde group of the glucose is oxidized. But in the process of oxidizing the sugar, the copper ion in the Benedict solution is reduced to this ion. The 2+ is reduced to plus. And because the sugar, presence of the sugar molecule is able to reduce the copper ion, this is called a reducing sugar. The sugar is being oxidized, but it is reducing the copper ion. So therefore, it is a reducing sugar. A test using Benedict's reagent turns brick red with urine sample. What might this result indicate? The brick red result indicates presence of 2,000 milligrams per deciliter of sugar in the urine, and that's what it indicates. Now this is a disaccharide. What are we? We are looking at a molecule of a disaccharide. How do we know that? There are 2 monosaccharide units connected using a glycosidic bond. So what are we going to do here is, what are the monosaccharide units? We will identify these monosaccharide units independently. What type of glycosidic bond? The 1,6 bond, that's what we will identify. Now we will identify the structure. Is it alpha or beta isomer? So those are the questions. So we will analyze. We will look at the first monosaccharide on the left. The OH group on carbon 4 is drawn above the plane. It is D-galactose. So I have to go back. So here, this is carbon 4. So here, the OH is above the plane. Galactose. OH is below the plane. Glucose. So we are now going, this is the first step, identify the monosaccharides. So we did, one is galactose, one is glucose. Type of glycosidic bond, the OH group carbon 1 comes from alpha galactose to the OH group in carbon 6 of glucose, which makes it alpha 1,6 glycosidic bond. So alpha 1,6, let us see. The OH is at the bottom, the H is on the top. It is the alpha isomer. Alpha, carbon 1, 6 glycosidic bond. So the first molecule is an alpha isomer. The second molecule also is an alpha isomer. So this is the alpha isomer of melibiose. So I'm going to say that the glycosidic bond is alpha 1,6, and the isomer, disaccharide isomer, is an alpha isomer based on this OH below the plane. So there you go. This is the alpha 1,6 bond, glycosidic bond, alpha melibiose, and alpha D galactose, alpha D glucose. Those are our answers for this particular problem. Cellobiose is a disaccharide composed of 2 D-glucose molecules linked by beta 1,4 glycosidic linkage. Draw the Hayward structure for beta cellobiose. Okay. Now I have to go back here. So please try to set this up So where are we going to start? We are going to draw the Hayward structures for 2 D-glucose molecules. And the glucose molecule, the first glucose molecule is a beta isomer. Beta isomer, the OH is above the plane. The final disaccharide is a beta isomer. That also tells us that the OH is above the plane. So beta 1,4 glycosidic, so both glucose molecules, the D-glucose molecules, are beta isomers. So these study check problem solutions are given towards the end of your book. So I would ask you to try to set up and check to see if you have the right answer. And if you have any questions, please let me know. Structure of polysaccharides. Which polysaccharide is stored in liver and muscle tissues? Let's guess, is that glycogen? An unbranched polysaccharide containing beta 1,4 glycosidic bond. Cellulose is the polysaccharide with beta bonds. These are the bonds that are not digested by humans, and we discussed that in the previous section, that these are only digested by grass-eating animals. So beta 1,4 glycosidic bond will be cellulose. Alpha 1,4, alpha 1,6 will be amylopectin and glycogen. So identifying those is also important. So reviewing, cellulose and amylose are both unbranched glucose polymers. How do they differ? Again, cellulose has beta 1,4 glycosidic bond, and amylose has alpha 1,4 glycosidic bonds. And that is the main point on which they differ. Both are glucose polymers, but they differ in the linkage of the glucose monosaccharide monomers. Beta 1,4 for cellulose and alpha 1,4 for amylose. Okay.